All right. Well, this was measurement uncertainty and detection limits. I think it's perhaps the other way round, but I have a subtitle for this. We are at the edge of reason. That is, we are near what we can reasonably think about. I'm going to talk a little bit about, well, actually quite a bit about detection limits and what they mean, and some of the misconceptions that appear in connection with detection limit in particular. And then I'm going to talk a bit about measurement uncertainty near the detection limit. I'll wrap that up with a little speculation about whether measurement uncertainty is an alternative to detection limits or a supplement. The basis of detection limits comes from the idea that we've got an analyte, we've got something that we want to measure, we've got analyte at a particular concentration, it generates a signal. Now, as the analyte concentration gets lower, there comes a point where our signal doesn't reliably distinguish the concentration from zero. So we're not really quite sure whether we've got analyte there or not. Now, that's particularly important when you're analyzing to support regulations for a banned substance, one that's not supposed to be there at all. So there's quite a lot of literature in the past about how to put limits on what we can detect, what we can't, and how well our measurement method performs in this region. Now, the current international definitions, and if you like, consensus, if there is one, on detection limit, largely come out of considerations from AOAC and IUPAC, particularly in the 1980s, and that eventually found their way into international standards, particularly ISO 11843. The basis of those, you're an analyst, you're sitting at the bench, you get a result near zero. You think, well, that's great. I can detect anything right down to here. So my analyte concentration could be down there and I'd definitely see it. Well, maybe, but if you do your job properly, you might do another check and, oh, well, maybe we can't quite rely on that first result. And well, hang on a minute, that one's even closer to zero. And oh dear, some of these are below zero. Clearly, what we've got is not an exact result. We've got a distribution. We've got a spread of results for our blank sample that mean that we're not quite sure what a result means when it's close to zero. Now, the first thing we can ask sensibly is we've got a distribution or some set of results. At what point would we say that signal, and this is in the signal domain here, at what point would we say a signal is significantly above zero? So we can put in a probability, and it's usually 5%, doesn't have to be, but it usually is. And that thing generates a critical value. It's actually the upper tail of a one-tailed t-test. So if you've got a lot of data, that's at about 1.65 times the standard deviation. I've put that at zero for convenience. In fact, there can be a baseline offset there, but I'm assuming that's been corrected. So we've got a way of setting a limit here, and the job of that limit is to say what results are significantly different from zero. Now, that thing that we've just defined is not a detection limit. It's a decision limit. It says if you see a result above that corresponds to an analyte concentration here, then anything above there's probably something present. But if we had a true analyte concentration at that point, we'd get a spread of results around that, the corresponding signal, and that would also be quite wide. The other important thing is that half of these results are below this critical value. So if we've got analyte concentration sitting here, and we use this critical value, we know that 50% of the time we'll declare our analyte as absent. The second question then is, so how far up here do we have to go before we reliably exceed this limit? And there is an answer to that. We need to move up about the same distance, usually exactly the same distance, in fact, is what's usually assumed, so that we've got a low probability of getting results below our critical value. And that thing there is actually called a detection limit. So that thing there is a detection limit, and it's a true value. It's a concentration of analyte. There's a difference between the two. The critical value is a signal, and you can convert it into analyte concentration if you like, but it's something you see. A detection limit is something that you say, well, the true analyte concentration has to be above there so that we have lots of this distribution above our critical value. So we have plenty of signal, in other words. And that's quite a big distinction. So one of them's a signal limit for making decisions. The other one is a true amount of analyte that you'll actually be able to see reliably. Now, because of the statistics, this one was at 1.65 sigma, and very often it's assumed that this has much the same spread. So we end up with a number here, which is around 3.3 times the standard deviation of blank signal, or signal for a blank, usually expressed in concentration units. Now, that leads to some interesting interpretations. The traditional approach to this, when you're again regulating for something that should be absent, is to say that anything below the critical value is not detected. A really important thing is that anything above the critical value is detected. It's a positive. And you'll notice that that's between the critical value and the detection limit. In other words, half the range between the detection limit and 0 is positive. And of course, this one's uncontroversial. Everyone would normally think, well, it's above the detection limit, therefore it must be a positive. And that is actually true. In fact, you can be a little bit more specific than that. You can say it's greater than 0 with greater than 95% confidence. In fact, no, you can say it's greater than the critical value with greater than 95% confidence. So it's even more. Now, not everybody gets that right. First, sometimes you have reporting limits in there and people say everything below that is not important. I don't agree with that, but most importantly, there's that message there. Anything above the critical value is a positive. That's quite often misunderstood. A common misinterpretation is that anything below the detection limit is not detected. That's not true. The other thing that I've come across that can make life quite difficult is that anything below the detection limit is seen as not a number. It's reported as less than. And anything above the detection limit is a number. Well, that's not true either. This is a number, it's a valid result. Anything in here is a valid result, unless your quality control has failed, of course. So these things can be reported. It's just that they've got an uncertainty that might be quite large compared to the value. So of these, actually, you'll notice that the whole idea of moving half a pixel from the left to the right, changing you from something you can't believe to something you can, is just unreasonable. They're all numbers, they all have meaning. There's never a really good reason to say, well, I can't give you the number. And that's particularly true of the reporting limit. That used to be set so that the uncertainty was relatively small, and analysts were encouraged not to report anything where the uncertainty was large as a fraction of the result. Well, this is a new world, guys. We're beginning to learn to treat uncertainty. So I think reporting limits don't have an awful lot of use, except as a general guide. Main point there, you get a result, it's a number, it's a valid estimate. It may have a large uncertainty, but it is a valid estimate, even if it's below the limit of detection or below the critical value or below a reporting limit. That becomes particularly important if you are going to use those data subsequently, because we can't average less thans. We can't score them in proficiency testing very easily. We can't add them. One of the really difficult conversations I had was with an analyst who had been sent some blank samples by the laboratory down the corridor. The laboratory down the corridor wanted to subtract the blank values so that they could correct for reagent contamination and so on. But the service lab refused to give them any numbers. They just said, well, it's less than something. And of course, that meant that the lab asking for the results couldn't do their blank subtraction. So all they could report was, well, if we do our blank subtraction, our number is greater than whatever we saw, which doesn't really make a lot of sense. So they actually needed the numbers. But of course, if we give them minus 0.2 milligrams plus or minus 0.3, that may be meaningless in terms of true concentrations, but it is an estimate. And we can subtract it, and it does have an uncertainty with it that we can use to expand the uncertainty of our result if we calculate difference or averages. So there's a general rule there. If you can report a raw observation and uncertainty, please do. Now, that was all about detection limits. That's a way of thinking about the world that has served quite well for quite a long time, but was really designed to cope with circumstances where you have a banned substance which is not supposed to be there at all. Quite a lot of substances, that's not the case anymore. They should be below a level rather than at zero. It's quite difficult to prove something's at zero. For things that come with numbers, as we know very well, sometime around the late 90s, our accreditation body said that there shall be measurement uncertainty. And we had a new world. Instead of looking at results and standard deviations and statistics based on the results we saw, we had this strange thing called measurement uncertainty. Now, that's kind of adapted. We've kind of worked out how to use that, but there are still some problems near zero. The first one is that we can get to situations quite quickly where a traditional uncertainty interval goes below zero. So we can have a number, as I said, 0.2 plus or minus 0.3 means that we've got a largish infeasible reason. Now that's not too bad for a statistician, because a statistician kind of knows what to do with that. But having impossible values is a bit of a problem for the definition of measurement uncertainty, which used to be basically an indication of where the true value might lie. And the true value can't lie down here because this is a concentration. So there are a couple of questions there. First, if that's impossible and we're averaging around here, what's the best estimate of the concentration? Is it still this line in the middle, or is it somewhere else? And the other question is, well, okay, if we cut this little bit off, then this gets a bit narrower. Does that mean that the uncertainty changes as well? Both of those are quite complicated questions, but the guidance that we've got in the Eurachem guide takes a fairly simple approach. It basically points out that if you take your usual T interval, then somewhat surprisingly, this was a 95% interval all the way out to below zero. This is also a 95% confidence interval, because it has the same probability of including the true value as that one did. The reason for that is that there was never any probability of the true value being below zero. So all the probability about the true value is up here. So if we just quote a simple truncated interval, we are still quoting a 95% confidence interval. So the simplest recommendation is, well, keep the result that you had. If you have to quote an interval, truncate it. The other wrinkle, I suppose, is that our guide recommends that you still report the original uncertainty so that people can use it. In other words, we don't adjust the uncertainty. Now, that's all very well, but that can go a little bit too far. If this is the, if you like, original interval, as our result gets closer to 0 and perhaps goes through it, we end up with a narrower and narrower interval. And at some point, that interval disappears completely. So we end up with a 0 width interval. An interval is like, the true value is somewhere between 0 and 0. That's what that means just here, because that's the upper limit that's just hit 0. Now, that's still a 95% confidence interval. And I'm going to leave you to work out why. I'm happy to answer that later. But it's not really a very sensible looking uncertainty interval. So we've looked at other approaches, and one of the most attractive, at least in philosophical terms, is our Bayesian approach, where you start with what you already know. Now, a really simple case here is that this will probably be called an improper prior, but we know that the result is not below 0. The true value cannot be below 0. The result can be. The true value can't be down here, but it can be anywhere to the right of 0. So we say, well, let's start by assuming that the probability of it being above 0 is the same wherever it might be. That's actually quite unlikely if you think about it, but we can talk about that later if you really want to. Now we've got some observations, and they give us, as it happens, depending a little bit on what you assume, they'll give us what's called a likelihood, which looks remarkably like our usual normal distribution. And if we combine those two, our prior information and our normal likelihood, or t likelihood, in fact that would be a t distribution, we get exactly what we had before. We had a posterior distribution, which is what's called, what a Bayesian would call a posterior distribution, which is exactly the same truncated distribution we had. There is there's a difference though in the Bayesian world. First, some Bayesian treatments would say, well, you've got a choice about the estimate that you use now. And one of the estimates that you can use is what you saw, but another one that's perfectly defensible is that you can take the average of this distribution. And what happens then is that your original observed mean value tends to shift upwards slightly. In other words, Bayes tells you it's perhaps a bit more likely that your result was higher rather than lower than what you actually saw. You don't have to do that. It's a choice, as taking the mean is always a choice anyway. So there's a number of choices that you have to make about what value you take, and the mode is also a possible choice. That is the largest value in this distribution, and that happens to coincide with your original mean value when you're a nice long way above 0. It also happens to coincide with 0 as this distribution shifts to the left. So it's not too badly behaved. It's just not always easy to find a mode. The other thing is that a Bayesian would usually, let me just go back one slide, a Bayesian would usually choose the interval, an interval that includes 95% of this area. So they typically include the narrowest interval that does that, and that is another truncated interval. But it has some interesting properties, because certainly for a relatively small number of observations, as the mean moves off to the left, particularly as it moves out below 0, the Bayesian interval starts to get bigger again. And it doesn't do that for high numbers of values, not for a long time. But one way of looking at that is it's saying, well, to be down here, your dispersion must have been bigger than you thought it was. So we're actually going to quote a bigger uncertainty. So that's actually also quite nicely behaved. And that is chosen just to give you 95% of our posterior distribution. So uncertainty reporting, there's a paper there, but the results of that ended up in the uncertainty guide in 2011. It's still there. Bottom line on measurement uncertainty on values near zero. If we've got an interval, our truncated interval, one that's cut off at zero, still retains the correct coverage properties. Our guide recommends that we don't change the standard uncertainty. This thing has a minimal bias on the mean. In other words, if we report a value at zero or above, one of the things we've done is cut off the negative values. If you averaged a lot of those, then the average would be higher than it should be. So that's what we mean by biased mean. But that's as little bias as you can get to without reporting negative values. The only trouble with a simple truncated interval is that it can converge to zero. There is a common sense answer to that. If you're that far from zero, something's probably gone wrong with your measurement. So please go away and measure it again. Bayesian intervals, more general, but distinctly more complex to calculate. There's a hanging question out there, which was perhaps posed by Mike Thompson maybe a decade ago. Can we use measurement uncertainty to completely replace limit of detection? This one I think is worth thinking about. There are advantages. We don't have any cutoffs. We're not dividing the world arbitrarily into things that are numbers and things that are not. So everything's a number or with an uncertainty, and we generally know what to do with those. Our customers might not, but that's a discussion we have to have anyway. The other thing is the decision that we make is specific to a particular test item, because we've got a measurement uncertainty ostensibly for that particular test item. And that might include things that don't apply to, for example, simple solutions. Might be that we have homogeneity to take into account, which would have given us a bigger variation than we saw in our detection limit studies. So it might be quite important. But there is another side to the coin. First, measurement uncertainty is about a result. It's not a thing. It's not a statement about method performance. There's a lot of overlap, but particularly near zero, one of the things we often want to know is, well, does our measurement procedure reliably detect what we're looking for at the level it typically arises? Measurement uncertainty doesn't necessarily tell us that. Whereas a detection limit, in a sense, as a method validation parameter, the job of detection limit is to say, please don't go below here because you might not be able to detect something at all. So that isn't necessarily, measurement uncertainty of itself isn't necessarily what you want to know at the validation stage. We've already talked about measurement uncertainty near zero. It's a little bit more complicated. The traditional limits might include zero. There are Bayesian approaches that do work, but bear in mind there are also Bayesian approaches, for example, using a beta distribution, which is quite defensible if you're doing purity assessment, but actually is tantamount to the assumption that zero is impossible. So you can take a prior distribution which says that there must be something there. Once you've done that, your result will always be positive. And that isn't necessarily what you want when you're regulating for something that might be absent. Measurement uncertainty should be about the test item. Well, that's true. In practice, it's often about the procedure. So it doesn't, that advantage up there isn't quite so strong as it might be. And another minor wrinkle is that we usually quote two-sided measurement uncertainty intervals. And if you remember from the little diagrams earlier, all of the decisions were one-sided tests. And that means that our probabilities for decisions around using a two-sided interval, they're actually half the probability that we would have got. We're using a 97.5% one-sided confidence limit rather than a 95%. So there's a bit more chance of, a different chance of getting it wrong, put it that way. So the bottom line there is that measurement uncertainty and detection capability are not quite the same thing. Summary, I suppose. First, detection limits are based on statistics. Straightforward, as straightforward as statistics ever gets. A test for difference from zero and actually a power calculation. Where do we have sufficient power to exceed our critical value? They are not. Detection limits, the detection limit is not a decision limit. It's a statement about the capability of the method. Reporting limits, I'm afraid, are beyond the limit, and I'm not going to talk about those. General guidance, if you can report results and uncertainties, please do, because certainly when I'm doing statistics with them, I'll want the numbers, not less thans. It is possible to get uncertainty intervals for those. One day they might replace limits, but I think there's still a value in a detection limit as a method performance parameter. And that's why I think we might continue to need both. And that's where I'm going to stop. Thank you very much for your attention and for the privilege of talking to you.